Molecules have three-dimensional shapes, and it's easy for us to predict what shape the molecule has by looking at the Lewis dot structure and figuring out how the electrons will repel each other, because it is the electron repulsion that causes certain bond angles.
We've been looking at the valence bond theory so far, and valence bond theory is what gives us the Lewis dot structures and helps us understand bonding in molecules. Now we're going to look into something called the valence shell electron pair repulsion theory, which is often called Vsepr instead of using the entire words. When looking at the valence shell electron pair repulsion theory, it's really very simple in what it says. It says that the electrons that are in the valence shell of a molecule have negative charge, and so they repel each other. Because they repel each other, they try to get as far away from each other as possible, and the numbers of electrons or numbers of groups of electrons around an atom in a molecule will determine its shape. Now, when we look at what are the groups that we consider, it's either going to be a bond to an atom or it's going to be a lone pair of electrons. So what we do is we count up how many groups we have on that atom, and then from the number we're able to determine the shape. We'll start by examining two atoms attached to a central atom. When you have two atoms attached to a central atom, the electrons, whether it's a triple bond, a double bond, whatever, it doesn't matter how many bonds are there, it's one group of electrons between two atoms. Those atoms will repel the other groups of atoms, and they will try to get as far away from each other as possible. In order to do that, they go into this linear shape with an angle of 180 degrees between the two groups. So carbon dioxide, which is shown here, has two oxygens attached by double bonds. That's two groups. So how do they get as far away from each other as possible? In a linear shape. If I look at three groups around an atom, you can look here and you can see there's a central atom with three groups attached. How do three things get as far away from each other as possible? They go into what's called a trigonal planar shape with an angle of 120 degrees between each group. Now, if I look at this carbon in formaldehyde, you can see the electrons that are in the carbon-hydrogen bond, the electrons in the other carbon-hydrogen bond, and the electrons that are in the carbon-oxygen double bond all repel each other and get as far away from each other as possible, and so that would be 120 degree angles in a trigonal planar shape. The oxygen actually is interesting. If you look at the oxygen, you can see there are two non-bonding pairs, which are two groups, and then the bond to the carbon, which is a double bond. That is three groups on that oxygen. What's interesting is the non-bonding pairs would be at 120 degree angles to the double bond, just as the bonding electrons in the hydrogen are at 120 degree angles to the double bond. If I look at four groups on an atom, four things get away from each other as far as possible in a tetrahedral shape. So the molecular shape here is tetrahedral. The angle between the two groups is 109.5. Any four groups on a central atom will go into this tetrahedral shape. Now here it is four atoms with four bonds going into the tetrahedral shape. That's fine. Anything that has four groups, though, will go into this tetrahedral shape. An example is the ammonia molecule here. Even though there are only three atoms, there really are four groups. You can see that the nitrogen has a non-bonding pair plus three single bonds. The electrons in this structure go into a tetrahedral shape. You can see one corner of the tetrahedron has an electron pair. A hydrogen is at the other corner of the tetrahedron, and then the other two hydrogens are also at corners of that tetrahedron. If you were in higher level chemistry, we would say that this molecule has an electron geometry that is tetrahedral. But we want to look at the shape of the molecule. That means we examine the atoms only. And if we look at the atoms only, we see that nitrogen is rather puckered up and the hydrogens puckered down. That lone pair is actually very fluffy and squishes the tetrahedron down so that the angle between the hydrogens and the nitrogen is actually smaller than 109.5. It's down to 107 due to that lone pair, that non-bonding pair up there needing room to be. I can go to another model of 4 groups around an atom, and if I look at water here, you can see there are 2 bonds to hydrogens, that's 2 groups, and then 2 non-bonding pairs. 4 things go into that tetrahedral shape again. Again, we would say the electron geometry is tetrahedral. We're not going to worry about what the electron geometry is on an exam, though. Don't worry. At the corner of the tetrahedrons, you have 2 non-bonding pairs, and then you would have 2 hydrogens at the other corner of the tetrahedron. This makes the molecular shape, remember now we just look at just the atoms, the shape of the molecule, we look at the hydrogen, oxygen, hydrogen only, and we see that it is bent. It's actually bent far enough inward because those non-bonding pairs are very fluffy and they compress the bond angle of the oxygen, hydrogen, oxygen. It's actually smaller than 109.5 that we find in atoms with 4 atoms attached. In a tetrahedral shape, it's a very compressed angle there, isn't it? 105 rather than 109.5. But anytime you have an atom with 2 non-bonding pairs and 2 bonds to 2 atoms, you will find that the molecular shape is bent. To summarize all this, we can have 2 atoms attached to a central atom with no non-bonding pairs. That gives us a linear shape. 3 atoms attached to a central atom with no non-bonding pairs. That's a trigonoplanar shape. 4 atoms attached to a central atom. That gives us a tetrahedral shape. 3 atoms with 1 non-bonding pair attached to a central atom. The groups are tetrahedral, but the molecular shape is trigonal pyramidal. 2 atoms and 2 non-bonding pairs attached to a central atom. The groups are tetrahedral, but the molecular shape is bent. And what we're really focusing on is the molecular shape. Now, this is a simplification of the real Vsepr. We're not going into it anywhere near in depth that would include all atoms. We're trying to simplify this so that it's relatively easy to grasp so we can go on to other things. Using the principles that we've just gone over, look at the central atom and identify what is the molecular geometry of each of these molecules. Pause, do the problems, and press resume when you're through. To determine the molecular geometry of phosphorus tribromide, we look at phosphorus. The central atom, phosphorus, has 4 groups attached to it, 1 non-bonding pair and 3 bromines attached by 3 bonds. One of those groups is a lone pair. So the molecular shape is not tetrahedral. With the 1 lone pair, it throws it into a trigonal pyramidal shape. So we say the molecular geometry is a trigonal pyramidal shape. If we look at carbon disulfide, we can see there are 2 groups on carbon. 2 groups get as far away from each other as possible in a linear geometry. So the molecular geometry is linear. The central atom carbon has 4 groups attached to it. Those groups are tetrahedral. There are no lone pairs, so the molecular geometry is tetrahedral. Sulfur trioxide has, on the central atom, 3 groups: a double bond to an oxygen, a single bond to an oxygen, and a single bond to an oxygen. The 3 groups go into a trigonal planar shape, so the molecular geometry of sulfur trioxide is trigonal planar.